663 inches. Okay, and in real life, I know it's difficult to measure 8.663, so maybe you have 8.5 inch or you bring down to 8 inch. Okay, so that is for your, so this is for your horizontal nail spacing. Okay, so this is for, so this over here is equal to 8.663 inches. And then the next one,
Eugene,
yes.
could we just as well have considered just the top flange rather than the two
Say it
webs?
again. Say it again.
Could we have, to find this same spacing, could we have just considered the top flange rather than the two side small webs?
So the small web is transmitting less, it's distributing less shear force. So you don't need to put so many nails. Does that make sense? Right? Whereas the vertical nail is carrying a much higher load, you need to put more nails. You get where I'm coming from?
I'm just confused as why we started with the side, why we started with the webs and not the top flange.
You can start from the top also. Does not matter.
Okay.
Okay. Yeah, it does not matter. You can start from the top. The only things that are different is the first movement of area. Right? Right? That's not, yeah, it's only the first movement of area that's going to be different. Okay. So the next thing that we do, okay, let me copy the diagram again. Yeah, so let me copy this diagram, and I'm going to copy whatever that comes along with it. Right, so the next thing we're going to look at is the vertical, nail spacing. So the only thing that changed is you have to include this area now for the vertical nail. Okay, so the Q will be the Q of the small web plus the Q of the top flange. So we found our small web early on is 11.1288 plus by the width of the top flange is equal to 10. The depth is 1 multiplied by the Y bar is 3.3548 minus by 1 divided by 2. Okay, so this is equal to 11.1288 plus by 3.3548 minus 0.5 times 1 times 10 is equal to 28.548. So this will be equal to plus 11.1288 is equal to 39.6768. So from here is again plugging in the formula. Q is equal to V multiplied by first moment of area, which is 39.6768. So the values for all the the V and I are the same. The only thing that changed is the what? Is the Q. So for this reason, if we calculate S, is 110 by 33, 7.43 divided by 700 divided by 97.6768. Okay, so this will be 1.2149 inches of spacing. So this is for the spacing for the vertical nail. Okay, right? So because the first moment of area for Vy or for the vertical nail is higher, so the spacing, right, for the vertical nail, the S over here, the spacing over here is equal to 1.2149. Okay, so that's how you determine the spacing of the nail based on failure. Okay, any questions so far? So this topic is do you all find this confusing? The rules did not change, right? You still apply the 4 rules, right? uh, Q, the shear flow is equal to VQ over I. The shear stress is equal to VQ over IT. Nothing changed. The only thing that you learn, extra formula that you learn is this one. That's it. Okay. Now, then I'm going to go to the next section. Before I go to the next section, anyone, any questions so far, please? Anyone? No? Okay.
So we have the shear flow that's entering our beam and then exiting our beam, right? Should we always start where the shear flow enters and work towards where it exits?
So you usually start by looking at the vertical web. Okay, by looking at the vertical web. So the vertical web will usually the shear flow will start from the top, go down to the bottom. Okay. Then if the Vy is at the bottom, you go from the bottom, go to the what? To the top. Okay. So that's where the next section come in. Okay. So I'm going to start a new section now. Okay. So the next section that we're going to do, I hope that answer your question. Yes.
Yeah.
Okay. So now the next section is going to be shearing stress in thin wall over here. I want you all to pay attention to this is for thin wall section and thin wall section only. What we have learned so far, they're all what? Thick wall section. Okay, so this is only for what? Thin wall section. So the rule to apply, I'll tell you what is the change. Okay, so I more or less have introduced to it slightly to you already. So what is the change? So I did not copy the other. Go on. So in thin wall section, we classify it into 2 views or 2 configuration. Okay. So in thin wall section, okay, classification of structure are the first one. It can either be a box beam, right? It can either be a box beam or white flange, okay, or white flange. Right. So on your left hand side, what you see is a box beam. On the right hand side is your what? White flange. Okay. So what you can see, what is common between the two like what I told you. So first thing I want to highlight the length of the arrow, the length of the shear flow, length of the arrow, okay, is equivalent to the magnitude of the shear flow. So you can see at point A, this area, okay, that I'm highlighting now, this area, the arrow is shorter. Means the shear flow is what? Smaller. Okay. At the section over here, the arrow is longer. Longer means the shear flow magnitude is higher. Likewise for here, shorter and longer. Okay, you can see that for the white flange. So the only thing that is common between the box beam and the white flange is the vertical web, the arrows all are coming down. Yes or no? The vertical web, all the arrows are coming, wrong color to use. The vertical beam, all the arrows are coming down. You can see that, yes or no? Right, vertical beam, all the arrows. So that's the only thing that's common. On the flange, right, depending on if it's box beam, right, it will start from A and move outwards. Okay. And what the control is the what? Like what I told you before. You guys have seen this already. We've sketched a bit, so it should not be a surprise. The control is the what? The vertical web. Okay. So for this case, on the white flange is coming towards the what? Towards the center. Okay. So if you look at the previous example that we have drawn for this case, like we have drawn, this is not, you cannot see anything now, right? This is exactly how I introduce you unconsciously to make sure that you're able to sketch the what? Sketch the shear flow. Okay. So similar philosophy. Now, so for the thin wall section, right? The thin wall section, the thickness, right? So the formula, okay, let's review a bit. Okay, what are the formulas? Okay, so the formulas to apply for both of them is Q is equal to VQ over I, and the shear stress is equal to VQ over IT. No new formula is there, right? And then what is still valid? Okay, I'm like a tape recorder that is not working well. I'll repeat again, right? Again, rules are the what? Same. The only thing different is this. Okay, the only thing different is this. Okay. For both cases, okay, for thin wall, okay, for thin wall, the T is equal to T thin. So this is our T thin. This is our T thin. Okay, for this case, this is for T thin. Okay, so the T thin for thin wall is perpendicular to the shear flow arrow. Okay, anyone, any question? Right, so I'm going to do thick wall. Anyone, any question? Yeah, okay. Right, for thick wall, right, so I'm going to say T is equal to T thick. I'm going to use different color now. Okay, for thick wall, T right? T is equal to T thick, right? So for thick wall,